Great. Thanks everyone for joining us on the Thursday before Easter. So I'd just like to start by acknowledging that we're meeting on the unceded lands of the Ngunnawal and Ngambri people, and to pay our respects to the elders past, present and emerging. So today we're very lucky to hear from Paul Tregoning. So over to you.
Thanks. I apparently hadn't given a talk for about 5 years or so volunteered to do this and then realised a couple of weeks ago that it was the Thursday before Easter. So thank you for turning up. And I'll try not to talk too long. What I'm going to talk about today is some of the work, some of the results that we've come up with in our group over the past 5 years, since you haven't heard from me for about that period of time. We've been doing things with space gravity, satellite altimetry, glacial isostatic adjustment models, all sorts of things, some of which some people might know bits and pieces. Some of you may know nothing about it at all. We'll see how we go. So what is geodesy? Size and shape and gravity field of the Earth. They're the three classical pillars of geodesy. Built into that is needing knowledge about reference frames, coordinate systems. In basic terms, latitude, longitude, and height is a coordinate system. You can then convert that into a XYZ Cartesian coordinate system. And that's what we do in geodesy, but we do it at very, very fine, high accurate scales of millimeters. We need that so that we can calculate satellite orbits accurately, so that we can know where the measurement was taken, what the measurement was of. Geodesy is an observational science. And the time variability of gravity is of geodesy is what's important in an earth science sort of context, where we can look at crustal deformation, which relates to plate tectonics, interseismic, coseismic, and postseismic deformations. Slow slip events on subduction zones were first really discovered by the fact that the surface of the overriding plate was deforming. And this is because of slow slip that was happening at depth. There's not really any other way that you can detect that. Elastic deformation of atmospheric pressure loading, hydrology loading, and ocean tide loading. When it's high tide at Bateman's Bay, Canberra goes down by about 8 millimeters. When there's a high pressure system comes across the ACT, Canberra goes down by probably 5 millimeters. So we talk about terra firma, but it's not firm at all. It's deforming all the time. The solid earth tide, as we call it, the effect of the sun's gravitational field and the moon acting on the earth, means that the earth is doing this all the time with an amplitude of about 40 to 45 centimeters. So we're not on stable earth here. The earth is constantly moving in all sorts of directions. Glacial isostatic adjustment is another part of it. Crustal uplift, the isostasy adjustment of the Earth to massive changes in load because of ice sheets in the past. These have gravitational effects, and I go into this in a bit more detail in the talk later on. And then we get to change in the Earth's gravity field, which is more the climate type part coming from the space gravity missions, melting of polar ice sheets, and that water going into the ocean, causing ocean mass increase. And then we have all the different bits and pieces and parts of the hydrological cycle. So all of this fits under the broad remit of geodesy, or applications of geodesy to the earth sciences. So what tools do we have to be able to do this? We have satellites, and they're fun. So I'm just going to go through in very quick detail what some of these satellite missions are and how they work, and then go into greater detail later on in the talk. First one is the gravity field, one of the three pillars of geodesy. And for this, we have the GRACE mission, Gravity Recovery and Climate Experiment. The key measurement of this mission, it's two satellites flying in tandem about 400 to 500 kilometers above the surface of the Earth. They're 200 kilometers apart, one following the other. And we measure the change in distance between the satellites with an accuracy of about 1/10 of the thickness of a human hair. which is absolutely phenomenal engineering, but it turns out to be pretty easy for the people who know how to do it. So with this measurement, we can measure changes in mass on and within the Earth, and that means groundwater changes, soil moisture, melting of ice sheets, increase of ocean mass, and things like that. Just quickly, the way this works, if you have an increase in mass in a location, like a flood in southwest Queensland, you've got more mass, more water sitting there. As the satellite comes along, it's going to be accelerated towards that extra mass. And then as it flies over it, it'll hover a little bit and then it keeps going. The second one does the same thing. And this changes the distance between the satellites. And we can measure that with great accuracy. So the change in distance tells us about the change in mass. Effectively, what's happening, that extra mass on the surface is causing a different acceleration to act on the satellite, which causes it, the way it flies to change. And it is embedded into the measurement. And so then we, through an inversion process, we can take those measurements and solve for the changes in mass on the surface of the Earth. Satellite altimetry works in a very different way. The measurement here is the time for a signal, a transmitted signal, to bounce off the surface of the Earth and come back up to the satellite. So if you know where the orbit of the satellite is, if you know the height of the satellite relative to the center of the Earth, and you know how long it took to go down to the Earth and back again, you can work out that distance from satellite to Earth, and therefore you know the height of the reflecting signal with respect to the center of the Earth. So if that reflecting signal is the ocean, then you know the height of the ocean. If it's an ice sheet, you know the height of the ice sheet. From this, if you take these measurements on a regular basis, then you can get the change in height of that surface, which will give you regional sea level change, or integrated would give you global sea level. And the same thing with ice. Ground deformation is one that people are probably a bit more familiar with. Does anyone remember this cover of Nature back in 1991, I think it was? The Landers earthquake. This was from INSAR, Interferometric Synthetic Aperture Radar. And every rainbow pattern here, every fringe is 25 millimeters of deformation. So for the very first time, we had an image of the deformation of an earthquake in very good spatial scale. Now, this was the French solution. Massenet was the author of this paper. And JPL, Jet Propulsion Laboratory at NASA, were also working feverishly on this. And because of the size of their computer memory, they could only work on a chunk. So they were working on this bit here, and they had all these parallel lines of deformation, which also looks like orbit error. Orbit error has just parallel lines. And so they were working, trying to improve the orbits, and couldn't see what was wrong. The French had more memory, and their computer could do the whole thing and saw what it was, published the paper, and JPL went, oh my God, we were right. So from INSAR, we can get spatial resolution of surface deformation, which can tell us about what's happening at depth in the Earth. We can also, from GPS, get a time series of position. This is the northeastern vertical for Sampari and Banda Aceh, northwest Sumatra. And here you can see the co-seismic deformation of the Sumatra Andaman earthquake, then the Nias earthquake, and then the post-seismic relaxation that's occurring afterwards. We can learn all sorts of things about what the Earth is doing from geodesy. Okay, so for those in the audience, you remember Monty Python. What has geodesy ever done for us? Well, it's done lots of things. You depend upon it to find your coffee shop. Athletes in the room know their particular segments and how long it takes them to do them through Strava, which is also using GPS. Autonomous vehicles and so on, that's all kind of the navigation part of geodesy. In plate tectonics, there was about a 5% error in the geological time scales, which was confirmed once we finally got measurements of continental drift from geodesy. As I mentioned earlier, detection of slow slip earthquakes. I looked this up actually to check this before this talk. And back in the 70s, there were seismologists talking about slow earthquakes. I'm just looking for seismologists in the room. Not too many. But slow seemed to mean minutes rather than instantaneous. Correct me if I'm wrong here, Malcolm. What we mean by slow is weeks. So there are deformations occur in the Cascadia and the Higurangi Trench in New Zealand, where the slip occurs over weeks. And the surface deformation shows this. You get very non-linear motion in the GPS time series. Post-seismic deformation, again, as I showed in the previous one. And we can also identify regions undergoing interseismic strain. So when the fault is locked, be it a subduction fault or a strike slip or whatever, you get a buildup of strain, which means you get velocities measured that are not representative of the rigid plate. And that can tell you how much is locked and how much release might happen in an earthquake. In terms of climate science, we can look at global and regional sea level. Geodesy has been used, the combination of altimetry and GRACE, to identify errors in the Argo floats, so the steric computations of thermal expansion and salinity problems in the ocean. This was identified by having a third kid on the block who could find something wrong. We can quantify melting of polar ice sheets and ocean mass increase and so on. And then it goes into the continental hydrology, of which we do less of that here at RSES, for groundwater monitoring, tracking of floodwaters and the like. So here's a quick example. Global mean sea level measured from satellite altimetry, the black line here. Steric sea level integrated from Argo buoys. Global mass measured from GRACE. And when you add these two together, you get the purple line, which is the measured change in height. So now we can actually start to pull apart why sea level is increasing. Is it just thermal expansion? Is it because of increased water going into the ocean from ice sheets or groundwater resources or so on? And they should add up, because that's kind of there are only these three things involved. They don't always add up. And when they don't, like clearly here, it's not adding up. Then we have to delve into the different parts of each of those three scientific fields to find out which one is causing the inconsistency. Sea surface height change from 92 to 2019 from a NASA website. The broad picture that you see here is that it's orange. Okay, nearly everywhere in the oceans, sea level has increased in the past couple of decades. Now, it's not uniform. There are parts that are more red than yellow. There are some little bits that are blue as well. But generally speaking, sea level is rising everywhere. So if we look a little bit more at some of these missions, the GRACE mission was launched in 2002 and was decommissioned in 2017. GRACE followed on in March 2018 and is still running today. And the replacement for GRACE follow-on is the GRACE continuity mission, which is due for launch in 2028, which probably means 2029, but it's all a bit Trump dependent because it is a climate mission. This is what the satellites actually look like. They're about 6 meters long, they weigh about 600 kilograms. And inside them, you have all sorts of electronics, GPS receiver, and the K-band system to measure, the interferometric system to measure the change in distance between the two satellites. So this is a GRACE satellite. GRACE follow-on is essentially the same with some updates to the various bits and pieces of equipment. And in addition, for GRACE follow-on, they added a laser system. So this is a radar system to measure between the two satellites on GRACE. For GRACE follow-on, it's a laser system, which is about 100 times more accurate than a tenth of the thickness of your human hair. So we're getting down to really tiny measurements. And when the laser people came along and said, we'd like to put a laser on, the GRACE people said, sure, here's our satellite. You can't have access to the vector between the two because that's where our radar system works. If you can work out how to do it, go ahead. And they came up with a very clever solution, which was, if you know what a quanticube reflector is, if you have three orthogonal pieces like a cube and you cut the side off it and they're mirrored pieces, Any ray that comes in bounces off the three sides and goes back out exactly parallel to how it is. So what the laser people did was, you don't need the whole mirror, you just need the bits, perfectly orthogonal. So they put 3 little bits of mirror in there, and they made it so that the virtual apex of those 3 was exactly at the center of mass of the satellite, which was really smart. And for the Grace Continuity mission, there will only be a laser system, and they're using exactly the same mirror system so that they can access the center of mass. So Grace follow-on's in orbit. It's still operating today. Laser altimetry started with ISAT in 2003. It's a laser, so it fires a signal down, it bounces off and comes back up. And the spotlight that hits the Earth is about 70 meters in diameter. Can't penetrate clouds. There was only one satellite operating. There's still only one. ISAT was replaced by ISAT-2. And ISAT-2 is still operating. Now, they learned from ISAT that the slope across, so we talk in orbit speak, a long track is the direction of flight, radial is down to the Earth, and cross track is orthogonal to the long track. So the slope cross track affected significantly the measurements. And for ISAT, it's meant to measure ice heights. And so we wanted to know the change in ice height because of melting of Antarctica and Greenland. And that happens at the edge, and that's where it's steep. So ISAT had trouble actually getting the measurements that it was supposed to. So for ISAT-2, they used 3 pairs of lasers, and each pair has 2. And so you get 6 measurements cross-track, from which you can calculate the cross-track slope directly from the measurements that are made, and then you can use that information to process the data much more accurately. So ISAT-2 works really well. It was launched in September 2018, and it's still operating really well. We also have radar altimetry. The first one of these was the TOPEX Poseidon mission in 1992. Takes a 10-day repeat time. So it flies over exactly the same track of the Earth every 10 days. And this is the principal measurement for global sea level. After TOPEX was JSON-1, they put it behind, and it flew directly behind TOPEX. So there was overlap of the 2 missions, so they could calibrate one against the other. And they've continued to do that throughout time. I think we're up to JSON-3 at the moment. And then the new one is SWOT, Surface Water Ocean Topography, which is an INSAR mission. So up on the satellite, 10 meters apart, are 2 sensors that transmit and receive from the other sensor, from which you get an interferometric measurement of the surface of the Earth. And it's designed for a water mission, so it's got a very small wavelength. It's Ka, which is 8 millimeter wavelength or something like that. And it gives us measurements of water height. So if you have multiple measurements, then you can get change in water height. Now, this is just looking at some of the SWOT data down in the Southern Ocean. This is the kind of resolution that we're now able to see for ocean topography using SWOT. Callum is actually on the science team for SWOT. So if anyone has technical information they need, go and see Callum. This was something I saw at AGU in 2023. This is a measurement of an iceberg that turned over in the ocean. It's a bit like a pebble in a pond, and it sent out all of these ripples. Now, the amplitude of these waves is 4 centimeters, roughly. And it's clear as day in the data. So SWOT data over the oceans is giving 4 centimeter sort of accuracy. And the papers that are coming out now using SWOT for oceanography are saying they have an RMS over kilometers, often, RMS of about 4 millimeters. So it's absolutely brilliant. It's working really, really well. Okay, so if I now start looking at some of the the papers that we've published recently. In I think it was about 2017 or so, we came up with a new way of doing the analysis of the great space gravity data using the range acceleration. Now, I said we measure the change in distance between the two satellites. The analysis of the data is done typically with the rate of change of distance, or the range rate. What we did was take the time derivative of that and look at the range acceleration instead. And back in like 2017 or something, we submitted a little paper to GRL who basically said, hey guys, there's an alternate way of doing this, and it seems to work really well. And our third rejection letter said, anyone who knows how to do this knows that this is not how to do this. So we thought, okay, we're just going to give up trying to publish, and we'll just keep showing results and try to convince people that it actually works. And in 2020 or 2021, I think it was, someone else stood up at AGU and said, ANU's been rabbiting on about this for years. So we decided to have a look. And the conclusion was, yes, it actually seems to work pretty well. So then we went ahead and published our papers using the range acceleration. Now, the range acceleration that they provide directly from NASA is rubbish. It's like at the 100 nanometers per second squared level. The signal is actually at the 10. So it's like orders of magnitude of noise in the data. We worked out a way of doing the numerical differentiation that cleans it up. And when we use this green curve through here as being representative of our signal, from which we can then estimate the change in mass on the surface of the Earth. And it works better than using the range rate. And the reason for that comes because of the correlations that happen. So what's being shown here is, this is the correlation between partial derivatives of a single point on the surface of the Earth with respect to the measurement. And what it's showing is this north-south striping pattern here, which means that any mass change at some location here, you could actually change the mass anywhere along that line, and mathematically it would look the same to the solution. The solution wouldn't be able to really tell very much the difference. You could also put a negative change in mass beside it, and that would have the same effect. Now, with the range acceleration observation instead, it's still there a little bit, but it's much, much smaller. So it decreases significantly the correlations between parameters. This is the estimate of the range rate for a particular month, and this is the estimate of the range acceleration. And you can see the north-south striping that comes in here. It's much, much reduced when we use the range acceleration. So here are the range acceleration residuals for December last year. This is essentially what goes into our least squares inversion when we solve for the parameters to represent the gravity field. Now here we're using what we call mass cons, mass concentration elements. So we break up the Earth into a bunch of tiles, which are roughly 200 by 200 kilometers. And what we estimate is the change in water thickness required over that whole 40,000 square kilometers, so that the gravity field changes to match the gravity field that the satellites flew around. So X hat here are the adjustments to our mass con. This is the change in water thickness on each mass con. The A matrix here is our partial derivatives relating our measurement, the range acceleration, to our parameters, the mass cons. We have the observation uncertainties, which are the range acceleration uncertainties, a regularization matrix to stabilize the inversion. And then the B matrix over here is the observed minus the computed, which is essentially this. So this is the difference between the observed range acceleration and some computed value using our starting point for the mass cons. So what we need to do is find adjustments to the mass cons so that the observed and the computed become the same, that this effectively drops to zero. So that's what we start with. When we do the inversion, this is what we come up with. Now, it's not a perfect match onto another, but you can see that the large signals here are all being picked up. So this is being absorbed into these mascons. This blob here becomes this blob in Northern Australia. This bit here becomes the adjustment to the Caspian Sea, which has dropped by about 1.8 meters or something from its 2000 value. And so it works pretty well. And we've shown through simulation that this actually works remarkably well. Now, if I put together a time series of what these range acceleration prefit residuals look like, then this is what you get. Now, the very strong stripiness that you see in here is because we've got orbital errors, which are causing once per revolution stuff. So just ignore that, look through that. And the rest of what you're seeing is hydrology and ocean signals. And up the top here, this red bit here is mismodeled glacial isostatic adjustment happening up here. So it works pretty well. You can kind of see the answer from the observations which we're putting into the inversion. And if I just pick just 1 month to look at, we can see some really interesting things in here. You see this sort of banding through here, through the Himalayas. We think this is errors in our a priori gravity field. So we're estimating adjustments to an a priori gravity field. And we calculate that to degree 180 in spherical harmonics, which means about 1 degree, so about 100 kilometer spatial resolution. And we think this is showing gravity field errors at less than 100 kilometer spatial resolution. You can also see, if you peer at this for long enough, you can see the subduction trench across here, runs through here and out into the Pacific Ocean. And there are some other subduction trenches that pop up in places. This bit here is the Sumatra Andaman earthquake, plus the earthquake that occurred near Cocos Island in 2007 or something. This is the Maui earthquake in 2010, Tohoku Oku earthquake out here. So these are the measurements. This is the range acceleration between the two satellites. And then you've got all this stuff down here in the Southern Ocean, which I was just talking to Adele about. If all of this stuff is signal, then this must surely be signal as well. So this has to be ocean mass change. And if I went back to the movie, you will see that this does change from month to month. So it's either ocean currents that are moving around, or it's wind-blown water rather than currents. But this is the kind of level of quality of data we can get from the GRACE follow-on mission that goes into the inversions for the gravity field. Now, the way that we actually do this, we use our mascons. We start with some sort of regular field where we don't care about coastlines or anything like that. These are just standard 200, 300 by 300 kilometer mascons. Then we break it into ocean and continent. Then we can pick out a drainage basin or a region or something, and then we can reshape those mascons into that part so that we get a particularly tailored, irregularly shaped mascon field. Now, we can actually represent the coastline with an accuracy of about 9 or 10 kilometers. Using spherical harmonics, which is the standard approach in gravity, you've got an accuracy of about 100 to 150 kilometers. So we're an order of magnitude better. And that means that we don't have leakage of the signal from the continent to the ocean and vice versa. So this is what you would get for estimating Greenland if you had mascons that actually cross the coast. So here we've got an estimate, which is an average of a little bit of ocean and mostly Greenland mass loss. If you use mascons that follow the coastline, you come up with a different pattern of estimate. This is the way we've dealt with this problem. Other groups estimating the gravity field have different approaches to it. We think this one's a good one. Some recent work by Beck McGurr was looking at sea level variations caused by continental hydrology. Now, this was the figure from the paper. This is the effect on the ocean from the continental hydrology in the grayed out areas. And this is the effect on the ocean from the ice sheets. The ice sheets win. There's much more impact from the ice sheets than there is from the continent, the non-ice covered continents, but there is still a significant impact here. The ocean is predominantly blue, so there is an increase in sea level because of continental hydrology, in addition to the ice sheets. Now, the way we do this is through what we call ocean fingerprinting. So a change in water mass on land has a predictable impact on the oceans. There are a couple of different ways it does that. We have fluid on a rotating Earth, and that will disperse in a particular pattern. But there's also what we call a direct gravitational attraction of the ocean water to the land. Now, the easiest way to visualize this is you think about a big ice sheet sitting on the coast of Antarctica and the ocean beside it. Because of that mass that's sitting up above the ocean is actually attracted towards it. And so it rises up towards the ice sheet. Now, if that ice sheet thins, you have less mass sitting up top, and therefore the gravitational attraction of the ocean will reduce and the ocean will actually subside. So as you get a melting of the ice sheet, that meltwater goes into the ocean, but the ocean beside it actually falls rather than rises. It's a bit counterintuitive. We call that the fingerprint. So we can calculate an ocean fingerprint. Now, for a meter loss on one mascon down here in West Antarctica, this is the ocean fingerprint for that single mascon. So you get about a little over 3 millimeter reduction in sea level right beside that mascon in Antarctica, and you get point something of a millimeter increase across the whole of the rest of the ocean in the far field. If you look at that in Greenland, similar thing, you get reduction around Greenland and increase in the far field. Now, if we do that for each and every land mascon, we can then calculate the effect on the whole ocean because of the changes in the land masses. And that's what's been done in these figures here. So the integration of all the Antarctic mascons plus the Greenland mascons plus Alaska, I think, equals this pattern. And the integration of the fingerprints of all the land mascons here equals the pattern that you see over here. Now, once we can do that, we can then look at the predicted, which is the red curve here. This is the predicted change in sea level because of the land hydrology changes and ice sheets. And the blue is what we actually estimate from the GRACE data. And you can see that they agree reasonably well. The black line here is the altimetry minus steric, ocean mass change. So these two should be the same because they're both measuring mass change of the ocean. The orange curve down here shows you the ice-free contribution to that, and the red dashed line here is the ice contribution. So there is definitely more ocean mass coming from the ice sheets than is coming from the continents. But this orange curve here doesn't have a zero slope. So there is at the moment, there is an ongoing increase in ocean mass because of loss of water on the continents, which is interesting. Now we can look at specific locations. So here in New York, and what we can do here is actually use the fingerprinting approach to work out which parts of the land are causing what effects in sea level at certain locations. So it turns out that this increase that we see in New York is coming from this blue curve here, which is Asia. So the loss of water in Asia is causing the biggest increase in sea level in New York, which is not what you would necessarily think is happening. If we look at Kuwait City, then it's again dominated by Asia, the decrease here. Now this is actually happening, you can see it up here where it's a bit sort of yellow around this area. So in the strait here, this decrease is coming directly from here, and it's actually being sourced from two places. One is the Caspian Sea that has lost about 1.8 meters of water since 2002. And the other one is the significant groundwater pumping that's occurring in northwestern India. So those two reductions in water on the continents are meaning it's a direct gravitational reduction of sea level in the Eastern Mediterranean and in this part of the Northern Indian Ocean. In Kiribati, out in the Pacific, there is an increase. It's again coming predominantly from Asia. So Asia is dominating most of these places. And then finally in Lagos in West Africa, it's the Africa. So it's the local effect that's having the biggest impact here. Now we can also look at the climate effects on sea level at short periods of time using the same approach. So this is the change for the 2010 to 2012 La Nina, which predominantly hit the northern part of South America and Australia. At this time, Australia just got very, very wet, as most of you here would probably remember. And this is the change in sea level because of northern South America. So this is the impact from here, and this is the impact from here. So Australia pulled 1.4 millimeters per year out of the global oceans, and it was all dumped on Australia. In the more recent triple La Nina, the rate was less, but it went over 3 years. And so the amount of water that was on Australia in that total time was kind of similar. But you can see for this one, the impact of the direct gravitational effect is more around the southeastern part of Australia, whereas here the whole of Australia pretty much got wet. We can do the same thing with groundwater extraction. So this is a very significant signal in the GRACE data, and it's causing this reduction in sea level in the near field, and it's causing an increase in sea level of about 0.1 millimeters per year in the far field. And a similar thing is happening in Beijing, where they've been pumping out groundwater. When they realized this, they stopped. And this is showing how a changing policy of how to use and interact with groundwater has affected global sea level effectively. Okay, if we move on to SWOT, then we get some really interesting results. This is the paper that was published this year in January or February. It's designed to measure the height of water, simply put, which can be oceans, lakes, rivers, dams. The required accuracy for the mission to be a success was about 10 centimeters for a 1 by 1 kilometer region and about 25 centimeters for 250 by 250 meters. So we wanted to see whether that actually applied in Australia and how well it actually worked. So it's all very well to have a mission requirement, but sometimes things work better, sometimes things work worse than expected. And in this case, it works better than expected. So here's a comparison of a in-situ river gauge with the height measurements from the satellite. And we get an RMS of the difference between the two of about 6 centimeters in this case. We looked at a number of different river widths and locations, and it ranged between about 3 and 10 centimeters was the RMS between the river gauge and what we could get from the satellite itself. Now, there are a number of rivers in Australia that are ungauged. They're not measured. No one really knows what's going on in those. And we can do it with this satellite now down to a river width of about 40 meters, I think it was, with an accuracy of about 5 to 10 centimeters. So this opens up huge opportunities for hydrology and land surface modeling. We can also use this to measure on-farm on-farm storage. And in the paper, we said it's an area in the Murrumbidgee. It was actually around the Hay area. We didn't specify exactly where it was. And we looked at 9 or so different on-farm storage areas ranging from 200 and something meters to the biggest one was about 2 kilometers by 3 kilometers or 1 by 2 kilometers or something. There are some massive, massive storage areas. If anyone's driven the Hay Plains, when you come out of Hay heading west, there's a section where you go past a big green wall bank, like an earthen bank. That's actually the wall of the dam. and it's about 2 kilometers wide. Given that we have an accuracy of about 5 to 10 centimeters of measuring the height, we can measure the height in the dam. And what we found is that this one, dam D, increased by 1.9 meters, which is about 32 megalitres of water was increased into that dam. And dam H was a 3.1 meter increase in height, which is about 5.4 gigalitres of water has gone into this dam. Now, we're not accusing anyone here of having stolen water. These agricultural businesses have water licenses. They're allowed to take water from the river under certain circumstances. In fact, at certain times, they're not allowed to, which is when river flows are quite low. That's when they're not allowed to. What we wanted to say in this paper is that there is a way of measuring how much water is in or has been taken out of dams at certain times. And we think there's a big opportunity here to help the government in terms of water compliance and knowing what's going on farms. So a traditional problem, or the way this has been done traditionally is with either logging. The farmers actually logged when they had their gauges turned, when their pumps turned on, for how long and therefore how much water, except they forget to record it. They also have propeller-based kind of measuring systems that measure how much water comes through. They tend to choke up because of frozen carp, apparently. So when the inspectors go along and find that it's blocked, it's a frozen carp in there, and the farmer says, oh, I don't know how that got there. What we have now is an external independent means of measuring with 5 to 10 centimeter accuracy how much water is in their reservoirs. And there's not a lot that they can do about it. So this hopefully will be a preventative measure that would encourage farmers to do the right thing, because they now know that someone could be checking them and they could be found out. So the conclusions of the paper were that it actually works really well over Australia. It works better than the mission specs. The products can detect water bodies down to 40 meters sort of size. And the ability to monitor these small water bodies opens up all sorts of opportunities for providing information in a hydrology modeling type environment where there's a complete absence of information sometimes. We have been waiting for the SWOT data to be released so we can look at what's been happening in southwest Queensland. Last week, Lachlan told me that it was released, and he's just run it through the standard kind of stuff that we do with this sort of analysis, and it threw out all the data. We don't know why at this point, probably because it's data of water heights over what is normally land. And so there's some setting that we need to tweak and change it so that it can actually recognize that this measurement over land is actually a measurement over water. So it's too early for us to be able to say how well we can do that. What we expect to be able to do is kind of map out the contours of water over hundreds of kilometers across southwest Queensland, and then also show how that water congregates into the channels and how it flows down into Lake Eyre, which is currently underway. Okay, PhD work that's coming from this. Lachlan, who doesn't have an image on RSES, but he's sitting right there if you want to know what he looks like. Lachlan is going to be looking at, can we use SWOT to improve the spatial resolution of gravity estimates? A quick example is Lake Superior in the US-Canada border. This is a transect across this line here. We're getting like 10 centimeters of height change across that. We can feed this straight in to constrain the mass cons for Lake Superior. KIT's going to be doing a very similar thing, but using altimetry data over ice instead of using SWOT data over water. Surface mass balance in Antarctica. What has Antarctica ever done for us? It's allowing us to go to Bateman's Bay. Otherwise, it'd be 58 meters underwater. It's contributed 10 millimeters to global sea level. It can be a source or sink of sea level variations, and it happens through ice discharge and surface mass balance changes. And in this study that we're going to probably submit next week, we're looking at total mass balance, surface mass balance, and ice discharge. And essentially, the change in total mass balance is the surface mass balance input minus the discharge output. We can measure that. We can model the surface mass balance, and we can measure the discharge. And so this should all close, only it doesn't. So here are the estimates of ice discharge. And if you look at the residuals for a bunch of different models, we decided in this paper to pick the one that gets closest to closing this balance, which turns out to be the RACMO 2-kilometre model. And so this is the one that we're going to be looking at in the paper. Beck has calculated the trend on a 0.25 degree grid across the whole of Antarctica, the trend in total mass balance, surface mass balance, and the ice discharge. And you can see the significant reduction over here in West Antarctica and also in the Totten area here. Now, the discharge here shows as positive, but that means there's a positive loss of ice. So that's why it's got the color that it has there. We can also, from these time series calculate, Grace and Grace follow-on measure the total mass balance. This is the RACMO solution, and the discharge is just total mass balance minus the surface mass balance. We can then look at the acceleration that's occurring in these locations. And concerningly, we see that there is an acceleration in West Antarctica. So the Pine Island and Thwaites and Smiths glaciers are losing mass at a increasing rate. There's also an acceleration in the Totten area, and that's actually coming from surface mass balance. So it's not coming from an increase in ice discharge, whereas the increase in West Antarctica is coming from extra ice discharge occurring. And this was a bit of a surprise. So the Totten Glacier is losing mass because of a reduction in snowfall rather than because of an increase of ice flowing out across the drainage line. The total Antarctic ice sheet time series changed behavior in mid-2020 and started to go up. So Antarctica started to pull water from the ocean rather than contributing water to the ocean. In 2024, that kind of stabilized, and now it's on its way down again. But there was a period for a few years where Antarctica was slowing down global sea level rise. The last paper I'll talk about is about glacial isostatic adjustment. What's it ever done for us? It's the ongoing adjustment of the solid Earth to changes in the ice and water loads. So if you think you've got a boat and you put a cubic meter of ice on the bow of the boat, what's going to happen to the boat? It's going to go down. The bow goes down and the stern comes up. As the ice melts, the bow will come back up slowly. Now, if the boat is sitting in honey rather than sitting in water, then as the ice melts, the boat will still come up, but it will come up slowly. And when the ice is all melted, the boat will still be coming back up. So the boat is like the crust, the ice is the ice sheets, and the honey, in this case, is the mantle of the Earth. And that's what's happening with GIA. So as the ice loads, the crust moves down, the mantle flows out to the side, and you get the peripheral bulge. As the ice melts, this still has to rebound up underneath. The GIA causes rise and fall of relative sea level. This affects tide gauge measurements. It causes the ocean floor to change, which affects satellite altimetry observations of sea level. It causes uplift and subsidence of the Earth's surface, which affects GPS heights and horizontal positions. And it changes the gravity field, which affects Grace and Grace following measurements. So it's either a complete pain for for Geodesy, or it's an interesting Earth signal that we have to look at. And various people have produced models to model the effects of GIA. In this paper by Lou, sorry, why is this hiding her face? We've developed a tool to assess the accuracy of those GIA models. And I'm not going any further. Okay, so Grace follow-on data records the ongoing GIA and the effect because of present-day mass change. GPS data records the ongoing GIA and the present day mass change, exactly the same signals. GIA models provide estimates of the GIA signals. So what we can do is put all of that together and actually assess the quality of the GIA model. So here we have the Grace spherical harmonic coefficients equal the elastic coefficients of the particular month plus the GIA contribution. Now we can replace this with a GIA model, which has spherical harmonic coefficients, and then we can extract out, if we subtract that from the Grace measurements, we can get the elastic component of the Grace measurements. We can take those elastic components and calculate with this equation the elastic height change that present day mass change would cause. We can do the same thing with the GIA part to calculate the viscoelastic deformation that it would cause. And then we can add them together to get the total height change that this GIA model plus the Grace measurements would produce. We call that a reconstructed height time series. And we can then compare that with what was actually measured at the GPS site itself. To put that in non-maths terms, we start with Grace. We have a GIA model from which we can get viscoelastic uplift. What's left when we do this subtraction gives us the elastic deformation, and that gives us our reconstructed height time series, which is like this. We can fit the rate through our reconstructed time series and fit a rate through the observed time series, and the error we define as being the difference between the reconstructed and the simulated. And so in this case, that would give us an error of 0.6. Now, if the GIA model is wrong, the viscoelastic component will be wrong, the elastic part will be wrong, and when you reconstruct the time series, it won't be correct. So we can use this velocity error to assess the quality of the GIA model. So here are two examples, one at Oslo and one at a site that no one can pronounce except Greenlanders. The viscoelastic GIA model is here. The GPS data is slightly under that. This is the elastic component. When you add them up, you get the blue side, the blue line. Over here in Greenland, there's almost no viscoelastic in this GIA model. It's all elastic, and it's actually still more than the GPS site is recording. So in both cases here, the GIA model has overestimated the viscoelastic velocity. We can look at multiple Grace solutions to find out whether analysis of the Grace solutions affects this. In this site, 4 different Grace solutions pretty much predict the same thing, and they're all different from the observed, which means that the GIA model here is wrong. Here's another case where 3 of the Grace solutions agree with the GPS site, and the 4th Grace solution disagrees. So there's something wrong with the amount of mass that's been estimated to have changed around this site in that solution. And the final one, all the 4 solutions diverge, and they're all different from the GPS site. So now we can use this tool and we can actually look at the change or the error as a function of spatial. And we find with 5 different GIA models, we get similar patterns here, which is suggesting that all of these models, the first 4, have too much mass has been lost, too much ice has been lost from the Laurentide, or that the lithosphere is too thick. Fennoscandia is similar, and Greenland is a bit all over the place, but there's similarities, like in the southeast Greenland, everyone has the same sign. So what we think we can do with this tool is actually quantify, or not quantify, we can qualify the accuracy of GIA models spatially. It's right here, it's wrong here, it's right here, and so on. Future work in the group is going to exploit SWOT data for things we haven't thought of doing with it yet. Ongoing Grace follow-on analysis for polarized sheet mass changes and continental hydrology. Preparation for the next space gravity missions, and exploit other forthcoming missions. EDGE is the next interferometric ice measuring mission. The next generation gravity mission is the European version of a Grace follow-on mission, and so on. Thank you.
We have a few minutes for questions. Erin.
Yeah, thanks, Paul. Really interesting. I had an interesting comment there about the Antarctic contribution to sea level rise, and that's sort of paused over the last few years. I was just wondering if you've been able to devolve to what extent that was a change in dynamic ice loss versus change in surface mass balance that caused that pause.
It was a very significant increase in snowfall. So it was surface mass balance increase that wasn't offset. Well, it's mostly around the edge, but I think it was everywhere. Yeah.
So you mentioned that this new way of measuring farm water storage could be, of course, really useful in monitoring. Have you had any discussions about that? Is there interest? Do they want to do it? Or do they not want to know?
Haven't yet. That's on my list of things to do this year, to actually go and take this. It's now published paper, so take it to government and say, look what you can do. Yeah. I don't know what reception we're going to get. But they can't actually stop it from happening because the data are public. Anyone can come along and do what we've done. We've published the method of how we did it. So any anti-farm lobby group can come along and do the same thing. Hopefully the government has matured to the point where they're willing to take this on now.
Is it too much to hope that perhaps with the high precisions involved, that one could see or come up with the start of an earthquake?
Yes, it's too much to hope. Look, there are some studies using the GRACE data for the Tohoku earthquake, where people claim to see a precursor for that. There are as many studies refuting it as supporting it. In terms of GPS, measurement of displacement of the surface, even when we know exactly when the earthquake did happen, and you look back at the data, you really can't see anything beforehand. So at this stage, you're probably better off with an elephant because animals can sense it before humans know what's happening. Malcolm?
I was just following up on the dam issue. Well, two parts. One is how often do you get a measurement of the dam? So what's the frequency of dam height measurements? And secondly was what's the amplitude of evaporation processes? So that might affect that compared with what you measure.
So it's every 21 days, the satellites fly over the same or measure the same thing. You actually tend to get a measurement on day 1, 2, then 22, 23. So you get 2 measurements and then a gap. That's the way the ground track pattern tends to work. The rate of evaporation, I don't have that number in my head. It doesn't affect the satellite measurement. It will just tell you this was the height of the water at the time that it was measured. Yeah. Evaporation will not cause an increase of 3.1 meters.
Right, okay.
Evaporation would cause a reduction. And
Yeah, last question.
So for that Indian site that was pumping out all the water, one of the issues there is the interception of Himalayan runoff by Chinese dams. Was there any sort of mass signal from Chinese dams in the Himalayas?
I don't know. I've never looked for that.
Yeah, because the Indians would say that that groundwater should be being recharged by the runoff, and that's just not getting there anymore.
I haven't heard that story about it. I've heard that it's groundwater extraction.
Yeah, it is
than lack of.
extraction, but it is extraction, but normally that extraction is recharged through that is the least of the Indians' position on it.
Okay, I thought their rate of extraction was increasing.
No, that could be true too.
maybe it's two effects.
So we're running out of time, so we'll leave it there, but feel free to stay around for self-serve tea and biscuits if you like, and let's thank Paul again.